In order to accelerate the exhaust to supersonic speeds, we designed and manufactured a pair of convergent-divergent nozzles at a machine shop in Purdue University. The nozzles were made out of chromoly steel, 4140 class, because of their high strength under heat. Two nozzles were fashioned out of two models for the exhaust flow. The larger nozzle was designed based on the theoretical properties of the combustion, while the smaller nozzle was designed based on the observations we made on previous tests.
And ready?
Yeah. There were a couple of interesting things to note on Test 7. First off, we can see the metal bluing from the heat of combustion. The ring itself is around 310 degrees Celsius, and from there on, each part of the metal continues to grow hotter. A thermal imager used on the nozzle after the test was complete indicated that the temperature exceeded 500 degrees Celsius. We also see that the path of the combustion twitches a little. These twitches all happen in a single frame, indicating that the process is sudden. The twitches are also accompanied by a larger flame, indicating that some kind of small burst in the combustion caused the twitch. Furthermore, the nozzle appears underexpanded as the gas cloud extends wider than the mouth of the nozzle, indicating that the nozzle could have been made wider to make it more efficient. Unfortunately, exhaust velocity and thrust could not be collected. Since our last test, the stand we had been using had rusted somewhat. Though we removed rust and lubricated the stand again, the thrust readings were still unexpectedly low. The thrust sensor was unreliable, and since our velocity is based on calculations of the thrust, we do not know either. We can still track sparks moving across the 1 meter distance and conclude that the exhaust was traveling at a minimum of 240 meters per second, and from that assume the exhaust was similar to that of our previous tests. We happened to open up our combustion chamber early after Test 7 and got to see the still hot polyethylene, transparent and glistening with water, one of the combustion products.
Full power.
Okay, over time the pressure was going down.
Test 8 was a similar story. Again, the thrust measurement was unreliable, so no thrust or exhaust velocity was recorded. However, the expansion of the flame appears to better match the expansion of the nozzle in this design. The flame expands wider in this nozzle because the throat is also wider, allowing the exhaust to lose less energy on compression. Since we have no velocity measurement, we do not know if the flow was choked in this nozzle. You may see that over time the nozzle becomes overexpanded as the exhaust flame shrinks. This shrinkage is due to our oxygen tank running low, something that we discover next test. Finally, in both tests, you can see flames leaking out the back of the nozzle. This was caused by our manufacture of the nozzle not being exactly the same as the tapering on the tube that we use as our combustion chamber. As far as we can tell, it will not create significant problems to our tests. Our 9th overall test was a dud, as we ran out of oxygen midway through.
We are out of oxygen.
Once we resupply, in our next series of tests, we intend to remove the flame trench and fire the motor upright so that we will get far more accurate force readings. We will also attempt to utilize greater oxygen pressure to increase the thrust and ensure that the exhaust will choke.